Let me introduce our two guests, our two specialists from ANSYS. So Sebastian is an ANSYS Sherlock application engineer with the background in mechanical engineering. His focus in structural simulation, but also his experience in thermal and electrical application. He's responsible for the entire ANSYS electronics reliability ecosystem. And Sebastian is based in Germany and supports all European ANSYS customers. Our second guest is Andrew. Andrew has a background in electronics systems design, having spent a number of years working in the defense industry before moving into the electronics design and simulation industry, working for companies such as Cadence, Synopsys, and Dassault. And currently, Andrew works in ANSYS as a product sales specialist in the EMEA for show ANSYS PCB reliability analysis tools, and Andrew is based in UK. Okay, so now I will give the voice to you, Sebastian and Andrew.
Thank you, Thomas. So I'll just say a few brief words first. Sebastian is going to drive the workshop this morning. He's the important person. I will hang around for a little bit, but then I have another meeting to go to. So I just wanted to say good morning to everybody, and to say that if you do have questions that come up from this workshop, please direct them to Thomas, and Thomas can direct them to us as required. So Thomas has our full support, and we're in regular contact with him. So even though MESco and ANSYS are separate, we are very close partnered. So I just wanted to reassure you with that. Sherlock is a unique tool in that it is there to look at the reliability of your printed circuit boards. So Sherlock is a tool that is great for looking at the printed circuit boards and understanding how they will react reliably. So just to sort of emphasize, Sherlock is about reliability. Okay, and when a designer puts together a printed circuit board, one of the thoughts that he has, of course, is not only the functional operation of the circuit board, but where it's going to go, and how it's going to operate in that environment. And that's what Sherlock is looking to try and help you answer. So you've got the electronics reliability, so you'll be doing SPICE analysis, VHDL, Verilog, and so on to understand the functionality. But then you're actually also looking at the physical aspects of the board itself. So how it's routed, what components to use on there, what materials to use on the board itself, whether you use a standard FR4 material for the printed circuit board, or whether you have to look at something a little bit more complex. And that's really what Sherlock is looking at and helping you decide right from the start. So Sherlock is enabling you to look at the thermal management and the effects of thermal activity on the board, thermal expansion and so on. It's looking at vibration and mechanical shock and so on, and the effects that these environmental conditions, if you like, have on the printed circuit board itself and the components, and in particular the solder balls. Okay, and this allows you to, as an engineer, to design for reliability. So the question that we always ask is, or we say, is that reliability is the robustness of a design to the thermal, mechanical, vibration, and shock effects that could impact its operation. I believe you've probably all seen a Sherlock presentation previously, so I'm not going to go through a presentation, but I just wanted to sort of start on this note that this is what we're looking to try and help you understand right up from the start of a project, if you like, all the way through to the first prototype, through the test and out into the field. Okay, with that, I'll hand across to Sebastian, and say if you do have questions to go through, please don't hesitate to ask them. Okay, Sebastian, over to you.
Yeah, thank you, Andrew, and thank you, Thomas, for the nice introduction. Let me share my screen and get started with our 2 hours introductory session about Sherlock. I want to run you through an entire project by loading the EK data, do all the necessary definitions inside of Sherlock, run the analysis, check the results, and then I guess at the end we have time to do some optimization loop here. As already mentioned, please, whenever you have any question, interrupt me, type it into the Q&A section. You can unmute yourself and speak out.
Sebastian, during your presentation, I will check the Q&A, and if there is any question, I will just stop you and I will tell you, because I'm not sure if you will be able to do the same time, looking at the Q&A and doing a presentation. So I will help you in that manner. Okay.
Thank you very much, and please feel free to interrupt me, that we can answer questions right away. Okay, here on my screen you see Sherlock when you first open it. Basically we have here our standard options: project, CCA, libraries, tools, settings, help. Later on we will see that in this area on the left hand side we get some kind of our feature tree, all the necessary setups for our project. And here the big space on the right hand side, that's our working area where we can make our definitions. In today's training, I'm using our latest release, Sherlock 2021 R2. If you have installed or are planning to install some older release, all the basic functionality is the same, but there might be differences in the user interface. So some things changed. For example, here in the help section, that's very powerful. We have our user guides and our getting you started information. So I think that's a very good starting point. The demo or the training I'm presenting today is with our tutorial board, which is shipped with Sherlock. And if you go to the help section, here is the getting started with Sherlock. Basically, you have all the lessons and all the necessary files here in this documentation. If you click on any of the links, this will lead you to the ANSYS help. And there's a lot more information, especially when you then scroll down a bit to the user guides here. If you are interested in managing parts, there are some specific sections. For example, on the approved vendor list, it's a very, very important information for the beginning. I will tell you more about it once we start to import the ECAD files. But please be aware that there is all the information, including the Sherlock theory guides, which is a new section in Sherlock 2021 R2. We have all the background. What kind of formulas does Sherlock use when we run a solder fatigue analysis or a random vibe analysis? So that's all included into our new theory guides here. Okay. Usually when we start a new project, you simply click on project and import your ECAD files. So here are all the import options. Import ODB archive is maybe the most common one. ODB++ files are widely used today for manufacturing the boards. We use the same information, and the ODB file, the ODB++ file contains a lot of necessary information. So there's little manual work you have to do if you use ODB files. The same works for the IPC 2581. It's becoming a bit more difficult if you use other file formats. For example, we can read Gerber files, but you manually have assigned each Gerber layer to your stack up. So that's a lot of manual work. So what I would recommend is ODB++ files. That's maybe the smoothest workflow here. For today's presentation, I don't want to start with an entire new project. I simply pick a project I predefined just for the sake that here I simply added 2 circuit cards manually. So there's no files imported other than some slide here I want to present. Yeah, that's our agenda for this training. So basically when you use Sherlock, it is 5 steps you have to think of. The first step is loading the ECAD files. That's a very important step. We need to get the information about the board into Sherlock to even can start our analysis. Once this is done, we move on and match the information from the ODB file with information out of the Sherlock library. So the material data is not available from the ODB file, but in the Sherlock library, we know a lot about of the components which are used. And so we can match this information and add material data, lead patterns on the components, and a lot more information, which is very, very handy to run the analysis. And the third step is applying load cycles. So how is the board used in reality? Yeah, we have vibration loading, PSD curves, formal cycles, shock events, and yeah, we have to define the load cases here in Sherlock. We don't always have to do it from scratch. Normally, yeah, we have some standard requirements from our customers, so from standards which are in place in the field of application. We are designing our PCB board, and so normally once we define this load cycle, we can use it with every new project, and yeah, don't have to do this definition from scratch all the time. Once we have all the geometry, all the material, and the load set up, we can run the analysis. And you know, there are different kind of analysis in Sherlock. I don't want to talk about all of the analysis types. It's not enough time for today's training. I will concentrate on thermal cycling, solder fatigue, and the random vibe analysis. So that's two types. And random vibe is a FAA type analysis, and for example, harmonic vibe is basically the same, or yeah, ICT is not a big difference to running random vibe analysis. So I think if you know how to run the random vibe analysis, you are feeling fine for the other FAA type analysis here inside of Sherlock. And finally, yeah, we will check our results and yeah, see where are the hotspots on the board, how to improve our reliability for certain components. Yeah, because once we know how the board is performing, we can go back to our load steps. Maybe we want to make some changes to the initial layout of the components. We want to use other components. Maybe we want to adjust our load cycles a bit. You know, we can do this, run the analysis again, and then compare the results with our previous results. These are the different steps we want to go through. So let's start with our first step, loading the ECAD files. And therefore, yeah, if you start a new project, I would go for import ODB archive. Here in this case, I already have a circuit card defined, so I can go to the circuit card options here and import the ODB file. here. That gives you basically the same, the same next window. We just need to search for ODB archive. So click on Browse, select ODB++ tutorial, and select the TGC file in this case for the ODB++. We have some additional options here. We want to assign the stack up thickness. So in the ODB file, we have all the thicknesses of the different layers in our board, and we can assign the thickness automatically from this information. If we want to, we can include other layers. So not all the layers which may be present in the ODB file will be necessary for our analysis. So maybe you have some layer which explains that the potting areas. That's not necessary for our Sherlock analysis in the first step, but you can import these layers and then create the potting out of this layer information. So that might be very handy. And normally I would recommend to talk to the electronic designer, especially at the beginning when you start with Sherlock, just to know what information is in the ODB file, and if it's possible to bring additional information in the ODB file, which makes it easier for you to work together with the electronic designer. Thinking up with electronic design here, especially for importing the ODB file, makes much sense, especially at the beginning. And once you've finished your maybe third project, importing ECAD files runs very quick, very automated, and at the beginning that can be some kind of a hassle. So if you start with Sherlock, don't hesitate to reach out to us, to reach out to the colleagues at MESco. They will help you with importing your first ODB file, and you will see that which might be confusing at the beginning becomes very, very easy if you've done it 1, 2, or 3 times. The next selection here is process cutouts. That means cutouts are not automatically transferred from the ODB file, but we can say, yes, I want in areas where a cutout is presented, I want this to be in my 3D model for the FEA analysis. So I think that makes sense to switch to yes. In the tutorial board, there is no cutout. So it doesn't make any difference if I change this setting here to yes. Once we are fine with our initial settings here, I can click on Scan Archive, and now Sherlock checks what's in the ODB file. So there's several different blocks present, named description, functional block, part number, and that's purely the definition from the electronic engineer. So he decides what information will be saved to this ODB++ file. And what we can do is we can map this information to Sherlock fields in our parts list. So here you can see, if I scroll down a bit, that are all the properties for all our components on the board we can define. It starts with activation energy, applied current, applied duty cycle, and we have a field here for the part description as well. If I scroll down to part, here's the part description, and of course that makes sense. Here on the right hand side we have the preview, what's the content of this field description in the ODB file. And as I mentioned here, there's more information Yeah, in this case, it seems to be a resistor. It's a 1206 package. Yeah, that's additional information which might us help in the later process. Functional block, yeah, that's a sub-circuit's name. And the part number, which is, I would say, the most important field, yeah, because the part number gives us the information, what kind of part is it. We can search for this part number online and get the data sheet and get all the details. And basically the part number is what we use in Sherlock to match the information from the library. So we have a couple of 100,000 parts already in our library, and they are also stored with the vendor part number. If we now match the part number for this circuit card here with the information from the library, we just check if the part number is available. And yeah, here is one important thing you have to take into account when you first import an ODB file. Normally, customers use internal part numbers. You know, they have internal information in the PDM system, and so each component on the board have an internal number. And most likely the part number is your internal part number here. And Sherlock does not know how what this kind of part is, how this translate to the vendor part number. And in the there must be some way to enable Sherlock to link your internal number to the vendor part number. In many cases, there's not just one vendor for one internal part number. Maybe you have multiple vendors for the same component, and that's what we track in a so-called AVL, an applied vendor list. I want to show you how this works with the vendor list in a second. First, I click here on OK to make this assignment of the information from the ODB file to the internal fields in Sherlock. Now we get a quick summary of what Sherlock is doing now. As soon as I click Import Archive, so we add board properties, we add a stack up, we add the package, board outline, a couple layers, and then drill holes, cutouts, and everything. So let's click on Import Archive. That takes a couple of seconds. You can see now on the left side, under our circuit card, we get automatically all the files which are in the ODB files added. There is some inputs automatically created, the parts list, stack up, layers, pick and place, drill holes, net list, and the DFMEA, which indicates that there's something wrong with it. In Sherlock, you can see if things are fine, you get this green tick. If something's wrong, you get the red cross. But that's not an error message. It's more like a warning message. And this warning message just tells us that we don't have the right information for DFMEA, so a failure mode analysis. If we are not interested in any DFMEA analysis here, we just can ignore it. So that does not mean that something is wrong and all the results are wrong, but that just means that I didn't do the initial definition. So I need to go in and view my DFMEA data to fix this issue here. So don't be worried when something is not with a green tick. Sometimes you get question marks. That also means there's a warning. You can check the warning and see if that will affect the results. So here it's just no data has been entered. Okay, I can't run the DFMEA, but the rest is still fine. Okay, next thing I want to check when I load the ECAD files is I double click here on the layers. When I do this, I get the Sherlock layer viewer here. And yeah, that's a good way to check what kind of information came in. Does it seem right? For example, here, the blue line here is the outline of the board. Does it look right? Is it the same outline? Sometimes maybe if it's not such a rectangular board, but a board with some round shapes, maybe there are 2 less points in the ODB file, and the outline does not look right. On the left hand side here, you have the layers, and you can decide what kind of information should be displayed. So on the other layers, we have the outline, and if I toggle it and untoggle it, you can see that the blue line is my outline. With the components, we can hide the components on the bottom here. Now that's just a top view of the board. Very interesting is the features here. So sometimes when you have many components, it makes sense to hide the labels. Because you can get confused with all the black labels here if the component's very small and the board very big, then you only see some black writing. You can't read it, so you can hide it. You can hide the axis of the board if you want to. You can bring in a grid here. So that's just one way to display things. On the bottom here, we have some filters, and with the filters, you can filter for parts by size, holes by size, by labels. If you're interested, where's my component U9? Just type it in, click enter, and now you see just component U9. If you write in U10, no, it doesn't work here, just works in the other filter. What's important to remember, sometimes you don't see all the components and you don't know why. Just delete the label here and click enter again to get all the components back. So filtering is very good to concentrate on the important parts. I won't go to all the layers here, but the couple layers is an important one. You can bring in the first couple layer. Now we can see all of the components, and the green stuff is the copper. We can check if the copper here fits onto our the pads fit to the components here, and that's the first check. We come back to this a bit later. So layer viewer, very important to check if everything seems right, which came in from the ODB plus file. Next step, I usually open the stack up, and for the stack up, we can see all the different layers of the board. Here in this case, it's 11 layers. We have the thicknesses for each layer. And for the signal and power layers, Sherlock gets the copper amount for each layer. Here, the first layer is 17.6%. That's what we you have seen in the picture I showed you, all the green stuff, that makes 17.6% of the entire board. And with this information, we can predict material properties. And CTE, Young's modulus, and we get the same material properties for the entire board. You can see the combined values here at the top. Since there is no information on the laminate layers and the laminate material in the ODB file, Sherlock always assigns a generic FR4 material and predicts the material properties here. You have to manually check if you are using some different material and some different construction. So one way to do it very easily is simply select all of your laminate layers here by this button on the top, right click on it, edit selected layers. And now you are able to choose the laminate material here at the top, and different types for the vendor and for the type of FR4 material or laminate material. You can select here at the top. You can adjust the layer thickness, and you can change the default stack up here. So we have some predefined pre-breaks you can use. You can manually add additional ones if you want to choose the fiber material if you are using non-default stack up, and you can even bring in a conductor material if you have any conducting material in the laminate layers like through-hose or whatever. Okay, for now I just keep it by the generic FR4 material. Confirm that all the stack up information is right, and can move on to the next step, parts list. And here is the information of all of our components on the board. And it starts with the reference designator, the part number, part type, package name, location, manufacturer information if available. And you can see we have here some color coding. And that's a good indicator to understand where this information is from and if I can trust the information. So for example, here is the blue columns here. Blue means it comes from the PCB or the pick and place list. And that's information directly out of the ODB file. So if you are interested in the location, top or bottom, that's basically information which should come from the ODB file, because the electronic designer defined and positioned the component is on top or the bottom. So that's nothing we should store in the library, because the position can be different with every project. Some columns are orange. Orange means that's a guess. For example, the capacitor here was guessed out of the reference designator. C1 usually is a capacitor, and J1 is a jack. Q might be a transistor. That in most of the cases, Sherlock guesses right, but you can't trust Sherlock here. Better double check this information. Here on the package, we have some entries which are coming from the package database. The package database simply scans the package name and sees if anything similar is in our package database, and assigns them this information. So for example, here quite soon. So basically what we have now is we loaded our ECAD files, checked if the layout seems right, checked if the stack up is right, and checked the parts list, what components are on the board. The next step, we want to confirm this information by the Sherlock library. So let's go back to the database, here, to the parts list here. If we want to check if this component was used before, we need the vendor part number here as information to match it with the Sherlock library. Here at the top, you see this. I can update the part list from the part library. You can do the same if you right click on the parts list and say update part list from the part library, and you can select single components and do this part library update as well here. And yeah, in the chat regarding vendor list and part numbers, we do have multiple vendors under a single part number, sometimes up to even 10, and that is confusing. Yeah, that is a very good question. And yeah, how we handle this is in Sherlock. If you go to libraries, so basically you import with the ODB file here an internal part number. So however your internal part number look like, it is listed here in this field after the import. If you now go to libraries, to the approved vendor list section, you can select or store your internal part numbers with, in Sherlock, we keep track of up to 4 vendors. Normally Sherlock just checks for the first one, assuming that the component is the same, so there's no difference in the reliability of the component for all the up to 10 vendors, then it doesn't matter which vendor part number we use in Sherlock. And yeah, that's basically how we can store our parts. Let me edit one selected part here. Just type in your internal part number, your description, the vendor name and the vendor part number, then the second vendor name and the second part number, and so on. Up to 4 vendors can we track here in Sherlock. And of course, you don't want to do this manually for all of the components. So the way to go here is simply export a CSV file from your PDM system, which has all the internal part numbers, description field, and then vendor name and vendor part number as separate columns. Go to import parts, select your CSV file, and import this information. So that is very, very easy to import all the approved vendor list information. Once this is done, you can select all of the components again here. So Control A works here in the parts list to select all the components. And then you can update this parts list with the information from your AVL. And then this will give us the link between the internal part number and the external part numbers. And once we say update parts list, we're able to select all of the parts from the Sherlock part library. One important thing here is the matching part number and manufacturer, or part number only. In this case, we didn't import any manufacturers with the ODB file. So we can't match part number and manufacturer. So normally we just select part number only, and then Sherlock will take the first component which is defined in the AVL list and matches this vendor here. And as I mentioned before, shouldn't be a problem for us, because in we are assuming that for one internal part number, we get exactly the same part. It doesn't matter which vendor we order it. If that's not the case, the part should have a different internal part number to identify it. Okay, so in this case, I don't need this AVL matching, but yeah, I already have the vendor part numbers available, so I can go directly to the update the part list from the part library, from the Sherlock part library, or for any local part library. So here you can select which library. As I mentioned, that the Sherlock part library is shipped with Sherlock, is very extensive, so we have a couple of 100,000 components in there already, and the library is growing every day. But you can create your own part library. So if one component is missing, or you use some specific components which are not public available, you can create your local part library. More than one. I created one test library to do some tests with it. And then you just select which library you want to use. So you can do this checkup twice. Just check what's in the part library, in the Sherlock part library, and then check the missing parts for the local part library. I go for the Sherlock part library for now. Again, just check for the part number since I don't have any manufacturers. And then I simply click Update Parts List. That takes a few seconds, and I will end up with hopefully all the information on the parts. So here we see I successfully updated 221 parts. The part count is 221. So all the parts are now matched by the part library. You can scroll through the list. Everything is green, means the information is from the parts database. And so we know we can trust this information. There is validated information from the data sheets in here now. And so that is what we want to achieve. In some cases, not all of the parts are found. That's not a problem. You can, whenever there's one part missing, you can go to edit parts by right-clicking on the component and manually add the information from the data sheet, check if everything is right, and then save the component. So here in this case, you can see that's this capacitor. By right-clicking on the three dots on the right-hand side, we can see that the guessed value was now updated by the information from the parts database, and now it's green. So it is still a capacitor, but still the guess was quite good. In this case, on the package, we have the package length with thickness, which is important. We have the material assigned here. If I go to location, the location still comes from the ODB file here, which makes sense. The X and Y coordinate and the rotation and everything. That's information which is project specific, so I don't want to store this information in the library, but I still want to use the ODB information. We have the lead information. In this case, it's a C lead with a lead count of 2. Now, when I activate the lead modeling here and click on this cube at the top, I can bring in a 3D preview and check if everything makes sense, if the component looks like it should. And that's basically the level of detail I can get in here, and check if I want to model this part with this level of detail, that's how my FEA model looks like. You can apply changes here. As soon as you change something like lead modeling enable, you can see that this value is now changed to a user-defined input and not any longer from the Sherlock parts database. If you have done some changes, for example, for the lead geometry here, you can save what you have changed. When you do this, there is a message which pops up if you only want to change it for part C1, or if you want to change it for all the parts with the same part number. So you can see that here the part number is the same for the first 10 capacitors. So we can apply these changes for all the components. I cancel it here. Another thing we can do, we can confirm parts properties. So as soon as I apply any changes, the part is unconfirmed. And unconfirmed parts can't be stored to local libraries. So if we are sure now we have all the right settings in here, we can click on confirm all part properties, and in the next step, use the library update. So to bring this updated information into one of our local libraries, click on this button here, select the library you want to update. So Sherlock part library is read-only. You can't bring in any new parts, but for the local part library, it's possible. Just update the library by the information from this part, and then you are able to use it with your next project. So that's, I think, a very important step to maintain your local library, bring in all the parts which are not in the Sherlock part library at the first place, and have them available for your next analysis. Here, from my personal experience, it takes a few projects to get the components which are commonly used on your boards into your local library. So maybe when you first import the ODB file, check with the library, you can match maybe 80% of the components. So like 20 to 30 components might be missing. And then you create them manually, bring them to the local library. With the next project, maybe then just 10 components are missing, and that becomes better. And at a certain point, just completely new components which never have been used before in your company are missing, and so you can then match them, bring them in the local library, and it's not too much work once you have set up everything here in Sherlock with the first few projects. Okay, one last thing I want to show you now is once we updated the parts list, we need to check our layers again. So double click on layers here, bring in the layer viewer again. We might have changed some of the settings here. For example, U7 got a new shape here, and for some reason these components don't fit on the copper mask, and most likely that's a mismatch in the definition for the part. So the part has a length and a width, and we define it in our electronic design tool, and we define it in Sherlock. And in Sherlock, it's the common definition is that the length is the longer side, and the width is the shorter side. And the rotation angle is defined by the length to the x-axis of the board. If it happened that in the ECAD tool, the length is the shorter side, the component is rotated by 90 degree, like here. And yeah, that's something we want to check once we have all of our components in. We check here at the top layer if everything fits on the copper. So components at the top, first copper layer, identify two components are wrong. Right click on click on edit, edit components. Now right click on component U7. Right click again if you accidentally close the context menu. Rotate 90, do the same for component U8, rotate 90, and now everything fits here on the board. That's what we want to see here in our model. Then we can do the same for the bottom side, components on the bottom, last copper layer, check if everything fits, and at the end, save your changes. And now we are fine. So second step, confirming data is done. We have all the information in, we have the geometries, so don't have to worry about this. At this point, I want to show you more information. So as I mentioned, on the help, you can find, for example, under managing parts, how does the part library work? How does the approved vendor list work? And part list management, filtering components is very powerful. That's all information which is available for you in the help section. But if you learn more about Sherlock, I would recommend logging into the ANSYS Learning Hub, because there is basically tons of information about the different disciplines, the different projects we have here at ANSYS, different workflows, and there's a very, very interesting section about electronics reliability as well. Here, if you go to the structures section, under structures, that's basically all the workbench, mechanical, optimization information here. And there's a special section about electronics reliability. Click on this, will open a new window. And here is all the information, starting by basic training, going to more advanced topics, showcasing some applications. So we have workflows in place for trace reinforcement or trace modeling techniques, humidity, flexible PCBs. So very, very advanced topics here. Webinars are accessible, technical papers, case studies, and the what's new information on the latest release. Most likely you start with the Sherlock basic training. If I click on this, there is different sections here. Basically all I'm showing you today. And what I would also recommend is here in the quick start page, there's a ECAD import best practices. And let me open this in a PDF viewer. Basically, the entire import process of the ECAD file, everything I showed you today so far is here in this document, and which makes it very easy to handle. There's this flow chart yeah, once you imported your ECAD file, it worked. Everything came in right. Yeah, the first question, is the outline correct? Yeah, what does this mean? Just click on this yellow field, and now you get more information about how to check the outline here. What you have to press. Here's a measurement tool. You can and all the information is in place for the start. Very powerful. And yeah, I think the ANSYS Learning Hub in general is a great source of training and information for all the ANSYS products. So yeah, please reach out to your colleagues at MESco for more information on the Learning Hub if you don't have access to it today. Okay, yeah. So just checking the Q&A section, no questions right now. I think we can move on to the next step. Step 3, apply load cycles. Here at the top, we have the life cycle definition. And yeah, basically we have to tell Sherlock how this board is used in reality, or how our test cycles look like. So for example, you want to confirm a test scenario. Every day you have some thermal cycling. Every day you start the engine for 1 hour, so that brings you some harmonic vibration which lasts 1 hour every day throughout 15 years. Maybe you have some maintenance which comes with some shock event when you open the housing and close it again. So you have some shock impacts, but they only happen 3 times a year. And yeah, that's what we want to define in our life cycle. Most likely we have already some predefined life cycles. So clicking here on the life cycle definition, we can load typical life cycles here. I want to use one predefined one here. That's a real world life cycle of a water pump. Loading the life cycle, and when I now open it here, I open all of the folders. We can see that we have in our life cycle different phases. We call this phases. The first phase is shipping. Then we have an environmental phase, a pumping phase, and a filter change. So our PCB board is placed somewhere near a pump, and so when the pump is operating, there is some events. Here this fire symbol means that the thermal cycle. This sine curve means it's a harmonic wipe. This cube or dice is a random wipe event. These are the 4 types of events we can create here. And let me guide you through the definition here. When I right click on life cycle, edit properties. So that's basically the first thing I want to do. What's my life cycle definition? First of all, I have to give it a name, and it always makes sense to give some description here to identify later on what kind of event is this, when to use this life cycle here. And here, basically what I have to define is the reliability goals. So how long does this board, how long is it used? What's the service life? In this case, it's 4 years. If you're running a test cycle, maybe you want to go down to some hours or whatever, how long your test cycle takes. And the next thing you want to define is the reliability metric. So the probability of failure. That's some information which is coming from maybe the reliability manager who says within the service life, we can only replace 3% of our boards. Other than that, that's a big problem. And in electronics reliability, we always talk about the probability of failure. So if something went wrong during the manufacturing process, your board might fail right at the first start of the machine. And that's why there is a slight probability that a board is failing right at the beginning. And we want to make sure that the probability of failure after our service life is not higher than allowable tolerance. So it does not affect the results. So if I change the reliability metrics here to 10%, for example, does not affect the results Sherlock is calculating. It affects the safety factor, or Sherlock will indicate components which are critical in red, and these components are very close to fail here for this reliability metrics. Of course, if I change this to 10%, less components will fail within the 4 years, and I see more green in my results. Just to be aware, that this value is very important to rate the results, but it does not affect the results itself. So that's the first thing I have to think about. How long is the board used, and what's my reliability goal? Click on save. Then we go to the next section here, our first phase, shipping. So the first use case of the board is I have to ship it to the customer. And when I right click on shipping, edit properties, you can see that this phase is defined as, with the duration. How long does it take, and how often is this phase repeated in the entire life cycle? So all the events in this phase are multiplied by the number of cycles of the phase itself. So the duration is 1 day, and the phase is repeated 3 times. So that means that the entire shipping process lasts for 3 days. And the events in this shipping phase, like the random vibration in X direction, double clicking on it will open the random vibe editor here. For each event, we have basically to define 2 things: the profile itself, and again the duration and the number of cycles, how often this is repeated. Let's start with the profile here. Edit profile, simply type in the PSD curve, how it is defined in the requirement sheet. So we have the frequency, we have the amplitude in G square per hertz, and yeah, that's the random white profile. When we run a FAA analysis, this profile will give us a certain number of strain on each component as a result, and therefore we get some damage when I run this random white profile. And of course, you can set the load direction. Here it's the X direction in the profile, so the load direction is X. For Y and Z, I simply use the same profile or use different profile, but then change the load direction here. And the same is if it's has some angle to the X, Y, and Z directions here. With this profile here. Let's go to the thermal cycle here for the shipping phase. Again, first we have to define the profile here from the minimum temperature. It starts like 6 hours at 15 degrees. Then we ramp up, which takes 6 hours again to 45 degrees. It's cooling down a bit to 35. And then after 24 hours, we have 15 degrees again. So important, the cycle has to start and end at the same temperature. So we start at 15 degrees, so we end at 15 degrees. And herefore we have 24 hours. And this 24 hours, the number of cycles. So basically, shipping is defined as 1 day, repeated 3 times. That's 24 hours. That's exactly 1 day. So we only fit in 1 cycle, or what we can do as well. So here for the duration, we can put in the count. We can put in once per day, or we can simply say 100 duty cycle means that's 100% of this cycle. So if we know it runs always, then we can always define it as 100 duty cycle here. Just for repeating it, we can go to the properties of the environmental cycle. Here that's 1 day, duration 1 day, and number of cycles 100% duty cycle. Again, in this case, it means 100% of the life cycle definition. So basically, this phase environmental temperature is always there. It's every day of our 4 years. That's the definition here. For pumping, I can go into the properties again. And here we have the duration 1 hour. So the pump runs 1 hour and it is started 3 times per day. That means 3 times per day, every day of the 4 years of service for 1 hour. So every day, in general, we have 3 hours of pumping, and every day in 4 years. Let's check the harmonic vibe event here. Again, let's start with the harmonic profile here, edit profile, and simply define your acceleration in respect of the frequency here. So at low frequencies, we have higher G loading than we have on higher frequencies. And by the way, we can load and save such profiles here as well. So if you defined one of these profiles and you want to use it again, for example, for X, Y, and Z direction, yeah, you can save it, just a profile, type it in, and then give it a different load direction or different cycle time. Again, here our duration is 1 hour, and it's running 100% of our pumping phase. So 1 hour, that is exactly the same time that the pump is running. That makes sense. And yeah, so it is repeated 3 times by our pumping phase here. For the filter change, that's a bit different. So edit properties. Filter change just takes 5 minutes, and I have to change the filter once per day. Yeah, again, once per day over 4 years. And the filter change itself here is our profile is this full sine curve. We measured with some acceleration probes, and this shock just takes 10 milliseconds, and it's just repeated once every day. Yeah, for the first time, the life cycle definition might be a bit confusing because there's not just one solution how you should define a life cycle. There are always more than one cycle possibilities. If you say that the cycle runs 24 hours or once per day, yeah, is basically not much of a difference here. What I would recommend is, after you did your definition, go to the view life cycle option. So right click on life cycle, view life cycle, because here you have some graphical input, and you can easily double check if it makes sense what you defined. So like here, 4 years of service, that's 100% of our service life. And as you remember, we defined shipping is just the first 3 days. So shipping phase plays only a minor role here in the entire process. Whereas for the environmental phase, we defined it's every day, 24 hours. So yeah, that's 100% of our entire service life. Pumping was 3 hours per day. It's more than shipping throughout the entire service life, but not as much as the environmental. And yeah, filter change, that was also just 5 minutes per day. So yeah, that makes sense. And you can do the same for your events to check if the thermal cycles have the right impact of the entire service life. So the environmental one was 24 hours every day, and so 100% of the entire service life. And the others are smaller. Here's the harmonic vibe event, and yeah, random vibe event is just a very, very small impact seen on the duration throughout the entire service life. So yeah, that is what I would recommend. Define your life cycle, check here this in the life cycle viewer if it makes sense. Make changes to the settings if you are unsure, and compare it. If does it make a difference, and is the life cycle definition, reflecting the right time throughout your entire service life. Once you set up everything for the life cycle, right click on life cycle, save life cycle, then you can use it with every future project. So like I did it at the beginning, load life cycle here. If you start to create such a life cycle, you want to add a new life cycle, a new life phase, just click here and give it a name, give it a duration. If you have a life phase defined, right click, you can add a thermal event, harmonic vibe event, random vibe event, and the shock event here very easily. And as you can see, you can define more than one event in one phase. Okay, yeah, that was our third step. Apply load cycles. I think, again here, it is important just to play around with the settings a bit to understand how best set up the life cycle. There's always not just one solution. There are more ways to define it, and you need to feel comfortable with the results with the life cycle viewer. Again, here there's a lot of information available in the help section. Let me check here. Here's the life cycle management. Under this help site, you find all the information necessary to define your life cycles. Okay, but now basically we are ready to solve our analysis. We have all the EGET files, we have the information on the materials and the leads. We have our load cases defined. So that's all it takes to run the analysis. And when I go to the analysis section here in my Sherlock tree, you can see all the different analysis types which are available. So cath failure analysis, that's basically a check on the design of the board. If there are any drill holes very close together, there might be some shortages in between the drill files. When you drill it, then you get micro cracks in the board, and this will lead to some electromigration and some copper bridges between the drill holes if they are too close together and carrying high voltages. So that's a design check here. Component failure is quite similar to semiconductor wear out. Component failure is on capacitors, semiconductor, of course, on semiconductors, but it simply checks if we have some reliability test data measurements from our vendors regarding these components. We can run tests if something will happen inside of the component. As mentioned, requires test data. Don't want to talk more about it for now. DFMEA is our failure mode and effects analysis. So how does a shortage in component U9 between pin 10 and pin 11 will affect the safety of the entire product? We can run this in Sherlock, but we can also export failure classes and part list information to ANSYS Medini to do the analysis in Medini, which might offer more options to do it. Harmonic vibe of course, is using our harmonic life cycles and run a FAA analysis, ICT analysis. Therefore, we need to define some test points and some ICT fixtures, but basically we can then run this bed of nails test and see if any components will already fail when we plug a connector in on the board, if we bend the board. All these manufacturing effects can be taken into account in the ICT analysis, and it will create a FAA model here. Mechanical shock uses the shock profile, runs the FAA model. Natural frequency, if I'm just interested in how the board will vibrate, do I need more mount points to attach the component? Then it's completely fine to run the natural frequency analysis. Plated through-hole fatigue checks if the plated through-holes will see some fatigue due to the expansion of the board in Z direction. So normal to the board, if I expand it too often, then the plating of the through-hole may develop some cracks, and then it's not guaranteed that the connection is stable anymore. And part validation just does a check if the information in the parts list is right. So if you haven't checked everything from the part library, then these components will be in the part validation. Interesting to see if there are any issues with the components, but basically when you checked your parts list carefully, if everything is from the parts list, then you basically can ignore this part validation. Random wipe, that's the analysis I want to show you in a few seconds, using the random wipe profile, running the FAA analysis, and then getting the results. Semiconductor, I already explained. Solder fatigue is the second analysis I want to show you today. What is the reliability of the components due to our thermal cycles? Thermal derating is a basic check on the rated temperatures. So every component comes with some recommendations from the vendors, like use it between -40 and +100 degrees. And we can check if in our defined thermal cycles here, we have temperatures outside of the rated temperatures. And then we will see that components failing. And the last simulation is the thermal mesh analysis. So that's basically creating a 3D model of our board and runs a thermal cycle, so the thermal expansion on it. As of today, we don't have any lifetime predictions for the thermal mesh analysis. It's just not, there's just no formulation available today. And we are doing research in the lab to find some link between our three-dimensional strains in regards of thermal cycling fatigue. So it's interesting to see how the board is warping, but we don't get any lifetime predictions out of this module here. So let's get started with the random wipe analysis. If we want to run a FAA analysis, one thing we didn't define so far is how is the board mounted? So how do we fix it? For FAA analysis, it's not possible to add any loads, but don't fix the component. So that would lead to a movement and no solution in FAA. So let us go back to the layer viewer once more. Bring it in here. Let me show all of the components. And here in the layer viewer, you have under the mechanical folder the mount points. You can again untoggle it to see where are the mount points. The mount points are the black dots, and there is an automatic mount point recognition out of the drill file. If we have drill files, drill holes with a higher diameter. I don't know exactly what's the threshold, but yeah, for drill holes like these here, Sherlock will automatically add a mount point, in this case a mount hole with yeah, the diameter of the drill. We right click on when we click on edit, select mount points here, we can easily edit this mount points. So for example, right click here somewhere in the middle, add mount point will give us this window here. We can name the mount point. We can select what type of mount point is it. Mount hole is basically, as you can see here, just a hole with a diameter, and we fix the red nodes are constrained. We fix the nodes here on the diameter of the hole. And here in the FEA settings, we can say X, Y, and Z direction, or just fix the hole in X and Y direction and let the movement in Z direction free. If we want to, if I switch this to the mount pad, it will create geometry here. And yeah, again, in this case, the blue dots are constrained, like I set my FEA constraints here. Since we create extra geometry, of course, we need material information, and that's here in the chassis material, aluminum. Yeah, all the mount point side, the height of the pad, and everything can be yeah, changed here, and the shape, if it is rectangular, if it is a slot, if it is a circular, or if the entire PCB is fixed, then we can use PCB here as well. Standoff, here we just constrain one point in X, Y, and Z direction, so it can rotate around this point. And the last option is a support pin, where we basically just constrain one node on our PCB board. These are the different options. Let me select the mount hole, and let me select, let it stay with slot. Of course, I can type in the exact numbers here, but what I often do is I click on save. Here you can see my slot, right clicking on it. Yeah, can go back to edit, can rotate, but what's also possible is if I select it and move it like I want to move it in size, here in shape, you can get the exact geometry. And let me delete the mount point, I don't need it here. Then we can multi-select if you press the shift button. So if I press shift, left mouse click, I can select all of the mount points, and I can, if I want to, by clicking Control and left click on one of the mount points, can select multiple of the mount points, edit the properties, or simply delete these ones as well to get just the mount points in the corners. Click Save, and now our constraints are ready. Next thing to do is go to the random pipe again, right click on it, edit properties, and that gives us this window here. We can set our analysis properties. So what's the minimum and the maximum frequency, our damping modifier. 0.2 is the damping we recommend for PCB boards. Of course, if you have done measurements and you have more information about the damping, you can adjust this value to the calculated damping in your case. If the test runs not at room temperature, but at some different temperature, you can insert the temperature here, and this is reflected in the material properties. Reuse natural frequency. If you have already a natural frequency results here, you can reuse this, save some time. Frequency range check will let you know that your input PSD curve uses a different frequency range here. Then next we select one or more of our random vibe profiles we defined here. Let me just check. I just want to use the set direction for now to see how set is affecting the reliability. But if you select more than one, you get combined results. And in the next step, we need to define how our model should look like and how we mesh the PCB. So for PCB modeling, we have different options here. Uniform means we just export one solid body for all of our 11 layers. If we use layered, one body for each layer is created. So we get 11 layers for the PCB with the right materials according to the layer materials here. For uniform elements and layered elements, we do something we call trace mapping. So we can use the information of the copper traces for each layer if we use layer elements, or for the entire board if we use uniform elements. And then we simply check for each mesh element what's the amount of copper which is in this mesh element. And this will then be reflected in the material properties, makes our analysis more accurate. And if our mesh of the PCB is fine enough, we get a good representation of the copper traces in the results. Next, well, let me change it to uniform to let it solve a bit faster. Next thing is element order. We have first order, runs fast, maybe not very accurate. Second order, and what I usually use is solid shell, because that's quite fast and still very accurate. So solid shell is a good choice here. Then we can select the mesh size of the elements in plane and normal to plane. So vertical is the mesh size across the thickness of the board. And what I want to choose is quartz, if possible. So that are the mesh settings. And so we can go through all the other settings, trace modeling. That's if you really want to model the copper traces. I didn't show it today, and normally trace modeling is nothing we want to use on the entire board. It's one of the advanced topics. Mount points, how should they be modeled and meshed? We have drill holes. If we really want to have the drill holes in the board, then we can enable this. Part modeling, that's an interesting one. We can filter out parts which are smaller than 6 millimeters, for example, and set the mesh settings for the parts. We can enable the lead modeling if we want the leads. In general, I recommend for random vibration or for all the vibration type of analysis to enable the lead modelings, at least for the bigger components, because the leads will influence the stiffness of the component and of the board. In some cases, maybe just the component is vibrating and the board doesn't see any effects. Then this will not be taken into account if lead modeling is disabled. For now, I keep it disabled. Go to the next steps: wire bonds, heat sinks, potting regions, and mechanical parts. These are all disabled. And again, these are advanced topics. You can in the layer viewer here, you can define wire bonds, heat sinks, pottings, and add mechanical parts if you want to For now, these are my settings. Yeah, the mesh is quite coarse for this presentation here, but gives us results very soon. As soon as I click save and run, now Sherlock creates in the background the input files for our ANSYS solver, runs the random vibe analysis, reads back in the RST file, and yeah, does the lifecycle prediction. Here in the task monitor, we can see all the tasks. And here the running task is right now the natural frequency analysis. Now it's running the random vibe in Z direction. So there's still something going on. When I right click on random vibe and select show location, then I get my Windows Explorer, and you can see all the files for the random vibe analysis. Here are the APDL, the CDB files. There is the RST file from the natural frequencies already, and yeah, errors, outputs. So basically all the information you might be interested in if you're a mechanical engineer. You can even open the model in mechanical, read in the results to do the post-processing in mechanical if you want to. In general, that's not really required. Yeah, we can do everything automatically here inside of Sherlock. Once we have results, we can see now there's a question mark. Double click on random vibe or right click show yeah, view results will give us here our results for the random vibe analysis. It starts with a summary, which indicates that just 2 components are failing. No, the others are fine. Remember, we filtered some parts out, so we didn't use all the 221 components here in this analysis. We have a log. That's the log file, the output file for the natural frequencies. We have the log file for random vibe, just in case there are any errors or warnings we are interested in. By Control F, we can even search in this output files. Next thing is our life prediction curve here. The life prediction yeah, it shows our 4 years of service and our 3% of failure probability. And yeah, the red curve is the failure prediction. And so we can see that after 1.5 years, we have a higher probability of failure than 3% already. By simply left clicking into this window with the mouse and drawing this bounding box, we can zoom in and see a bit more what's happening here in this area by right clicking, zoom out both axes. Oh, we should basically auto range will give us back our previous view. Very interesting is here this table view. Now we can see all of our components. We see that U9 and U10 is failing. We can get more information if we enable leads on the lead strains here. And the last tab is the question mark tab. What are our issues? And here, yeah, the random vibe, the PSD curve is defined starting with 10 Hertz. And we ran the analysis starting with 20 Hertz. So there's a mismatch in the PSD curve to our analysis. And the second warning is that the part validation was not successfully. That's in this case, in my case, it's because it is checking for the AVL list information. I don't have AVL list information here, so that's why it is failing. So I can ignore it as well. Important to remember, we now exactly know where our components which are critical, U9 and U10. Let's go back once more to the layer viewer here. Now we have a new folder, random vibe. which gives us information on the mesh we used. So yeah, very coarse mesh for the board. We get the score at the top for our components. So now it's easy to see that U9 and U10, the two BGAs, are the components which are failing. No issues on the bottom. Smaller parts like the resistors are ignored. We get the displacement of our board, and we can see that we have high displacement here in the area of the two BGAs. Maybe we need some additional mount conditions here to prevent the board from bending too much. We can get the strain results here for the bottom as well, and stress results. If you move with your mouse into the picture, you will see here in this area the stress value indicated. So if you're interested in learning what's the value, how high is the stress, just check it here at the top. That's random vibe. Solder fatigue, that's the second analysis I want to show you today. Right-click, edit properties. It's a lot easier to use. We just select the solder material here. We select maybe all of our thermal cycles, and that's all we have to do for solder fatigue. Because of thermal cycling, we don't create a 3D model and run a FAA analysis. We just predict the strain energy in each solder joint analytically. We have formulations which use all the information from the parts list. When I now click save and run, normally that's very fast. So we are getting our results here. Additional life prediction curve here for solder joint fatigue. After 2.8 years, we see a higher probability of failure of 3%. Again, go to the table view. We can easily identify the components which are critical. In this case, again, U9 and U10. The resistors here. And some others are close to being critical. So the time to failure is here. Some criteria we can use. Time to failure is 17 years compared to 4 years of expected service life. Right click on one of the components, do a life prediction. We can find this curve. We can see, still is fine, but maybe close to getting out of reach to create a higher probability of failure here. So it's 1%, more than 1%. So that's very close, but still okay. That's why it's yellow. The green ones, they shouldn't cause any trouble regards of reliability. We can only take we definitely have to do something to improve our board. But in general, now we have seen all the 5 steps. We have our results, and now we can go back to refine our setup. One thing I want to show, I think we have 10 minutes left here. For the solder fatigue, the resistors here is these CC resistors, so these chip components, and they are failing. When I go to the parts list here, I want to search for R1 just type it in here in the filters. Go to the top. That's the first one, R1. Edit parts, and these CC resistors, they are soldered to pads, and the pad size is very important to in regards of the solder shape. If I use a bigger pad, I will have a higher reliability of these components. If you click on this button, it's even possible not just use the recommendations from the datasheet, but read out the information from the first couple layer. So now we get the information our ECAD designer used here, and we increased the value here a bit. Let's see, in the width of the component of the pad is a bit smaller. So maybe I want to change back to the old value. So double click on the line from the parts database, and I restored my previous setting here. Click Save for all of the components. Then get rid of the filter again. If I scroll down to the resistors, we now have updated parts properties. Simply have to run the analysis again. If you want to compare the results, I simply save results here, my existing results. Of course, give it a good name. Here I just used the timestamp to compare them. Now you run to the solder fatigue analysis again. Run analysis task, use the same settings. Wait a few seconds till we have the updated results. And if we double click, we can see that the change in the pad properties didn't increase the lifetime a lot. Oh, it did for R1. Here, I didn't change it for all the other resistors. It seems, here for R1, I increased it by 2 years, 2.5 years, the lifetime. So using these pad properties didn't solve all of my problems. What I can do is now compare it against my previous results. And if you want to archive just the results, not just not the entire Sherlock project, I would recommend use this saved results, because you can open them in a Sherlock viewer. This Sherlock viewer doesn't require a Sherlock license, so you can install it on any computer and open the results. And here's basically everything you need to know about the project. The summary, live prediction curves. If you want to learn more about the random vibe, there is our random vibe curve. We have the results. We see the critical components. The same for the random vibe. And here, we can compare the results from Sherlock against the previous results. But there's more information on the life cycles, on the parts list. You can go in and view parts properties. Here you can check the stack up. You can check on the layers. So now we don't only have random vibe, we can identify the critical resistors here from the solder fatigue analysis. And basically all the information is here in one file, easy to share with colleagues to check the results, decide on some improvements, some changes in the setup to run the analysis again and check if you get better reliability with the new design iteration. Okay, I think and I showed you all the necessary steps to get your ECAD files, to use the Sherlock part library or the local library to update the part information with more properties, apply the load cycle and do the load cycle definition, run the analysis, and then finally check the results, do some modifications, update everything, and compare the results again. We have 5 minutes left, so I think that's a good good possibility again for you to ask questions. Anything unclear, anything I should show again, any additional topics you are interested in, yeah, please feel free to enter it in the chat or unmute yourself if you want to describe it with words.
If anyone of the attendees would like to make some comments by using the microphone, please write and message into the Q&A or just in the chat, and I will grant you an access to microphone. Okay, maybe from my side, one question, because I on one of your presentation, I showed that you can put an additional mounting point, and that should also change the results. Can you show how to put additional mount point if we not have any questions right moment? Or
sure.
Yeah,
sure.
Because that could be interesting.
Sure. So here in our results, we see that just mounting the board in the outer corners will lead to a high deflection here in the center. And one way to reduce it is maybe place a mount point here in the center. So it is quite dangerous because the closer the mount points are to the parts, that might affect the strains at the parts as well. But we can try it here. Click on edit, edit mount points. We can, for example, copy one mount point which is existing or create a complete new mount point. I just want to copy this one here, copy mount point, then I place it here. Okay, for now, maybe it's better to get rid of the red zone here. If I click on edit properties, I can go in and do changes to my setup. For example, I want to have it exactly in the center. So I go for X and Y 0. Save and save this mount point here. And let's go back to the random pipe analysis. Say run analysis task, use the same settings, save and run, and wait till the analysis is done.
In the meantime, we've got 2 questions on the Q&A.
Okay, yeah. The first question is calculate MTBF here inside of Sherlock. That's not possible. We decided it was possible a couple of versions ago, but we decided that MTBF is not the way we want to go with Sherlock, because MTBF uses handbook predictions, and with MTBF we don't take into account the real physics behind it. That is very interesting to use MTBF, and I guess some customers request for MTBF figures, and we can get the MTBF calculations in ANSYS Medini, so a different tool. There is a link between Sherlock and Medini, so we can basically hand over our parts list here. In the parts list, we have the failure class defined. So that's a property we can bring into the library. And so by updating the parts list here in Sherlock, we can hand over the information of the failure class. And in Medini, it's just a few steps to then get the fit rates or the MTBF numbers out of the military handbook Calcordia or whatever standard is here interesting for you. So MTBF not in Sherlock, but in combination with Medini, it's very easy to calculate the MTBF figures. And once you have your first part selection, you can then go on with Sherlock and run the real physics of failure analysis in Sherlock to get more accurate predictions of the lifetime. So let's go back to our layer viewer here. The random vibe analysis updated, and now we can see that the displacement changed by using this additional mount point here in the center. If I go for the strains at the top, we can see that we get quite high strains around the mount point. So but it seems we fixed our problems with U9 and U10. So using an additional mount point, if possible, would be a very good solution for increasing the lifetime for our random vibe analysis here.
Okay, I see, Sebastian, the last question on Q&A. So.
Is it possible to load test temperature profile from external file? It is possible. It's possible to load a profile here as CSV file, but it's not like a time-dependent file we can read in. It's just like these steps here. So we can export a defined profile here and load it in later on. When we have some temperature measurements or some thermal simulation, we need to think of the different ramps first, how we simplify this temperature profile. And but what we can do is we can use these temperatures for different components. So maybe the components on the outer edges of the board are not getting as high as the components in the center. Then we can define different thermal profiles for each of the components. So it's not just like I showed you today, like this typical oven test that all the components having the same temperature. Then we can import temperatures for each component and get different lifetime predictions, of course, for these components.
Okay, I don't see any additional question on the chat, so I think that we can end today's workshop. And I would like to thank you very much, Sebastian, and also Andrew, for doing this really nice and interesting presentation. So if there are any additional questions, please contact directly with me. And one reminder that you are able that we can generate for you a trial version of ANSYS Sherlock that you can start just to using it by their own and try to solve your problems with the Sherlock. So if you have any additional questions, please just contact with me, and I will deliver you all the data and we can work together.
I just want to add thank you for joining in today's workshop. Thank you, Thomas, for organizing everything, and looking forward to go in further discussions with you regarding Sherlock and electronics reliability in general. Have a nice rest of the day. Goodbye.
Thank you very much. Have a nice day. Bye bye. Ciao.